Hello and welcome to another NGen Math 8 lesson by eMathInstruction. My name is Kirk Weiler and today we're going to be doing Unit 3, Lesson 1 on Introduction to Transformations. Now transformation is kind of a big word, all right, and we're going to be getting into it in this lesson and this entire unit is all about transformations. They're amazingly important in geometry. You've already played around with them just a little bit, maybe, in some earlier grades, but this is the first time, or the first course at least, where you're really going to kind of dive into them full force. So, without further ado, let me bring this all the way over here, and let's kind of get into what a transformation is. All right, so very simply, what is a transformation? A transformation is a rule that assigns each point in the plane, or each point in a geometric figure, to another point in the plane, and it could even be the same point, all right? So let's just talk about this, right? So transformations are typically some kind of a rule, and that rule could be given to you algebraically, and we'll look at a few of those today, or it could be almost kind of verbal, like take every point in the plane and move it 5 units to the right and 2 units down, something like that. But the idea is that we would take all the points in the plane, and we will be concerned about ones that form some kind of object like triangle ABC here, and we will map them using some rule to somewhere else, all right? And that's a transformation. And transformations, depending on what kind of a transformation it is, have various properties. And that's what this entire unit's going to be about, is looking at different types of transformations, learning their names, learning their properties, and then connecting them with something we saw in the last unit, which was congruent figures. And we're going to be doing a little bit of that connection even today. But let's get right into it with exercise number 1 by taking a look at it. Exercise 1. Triangle ABC is shown in the diagram below. The original geometric object is known as the pre-image. Letter A asks us to state the coordinates of the vertices of the pre-image below. All right, so the original object that you begin with is called the pre-image. The one that you get after you transform it, not surprisingly, is called the image. What I want to know just right away is, where are points A, B, and C? So I just have to read the coordinates off of this grid. Let's do A together, then we'll have you do B and C quickly on your own. But point A, right, is 2 units to the right of the origin and then 9 units up. So it's simple enough for us to just say, all right, we've got A at the point 2, 9. What I'd like you to do is figure out where point B is and where point C is and write their coordinates down. That should be pretty easy. Why don't you go ahead, take a few moments and read off their coordinate points. All right, let's do it. Well, point B, right, we're going to go 4 units to the right and we're going to go 13 units up. So point B is at 4, 13. Point C, right, we're going to move 8 units to the right and 8 units up. So point C is one of those points where the x and the y coordinate are the same, 8, 8. Now again, we talked about this in the last unit. It is amazingly important for you to be able to very accurately read off these coordinates. If you're thinking, well, I had the right things, I just flipped the x and the y, that is not a minor mistake. You've got to get on top of that, and you've got to get on top of it early, given that you've been plotting points in the coordinate plane since 5th grade. 5th grade, that's when you start doing it. So we got to have these things down. Now, let's look at a transformation. All right, I'm going to bring this just up a little bit. Letter B. The following transformation rule is used to map triangle ABC. And here we have x, y with a little arrow, x plus 5, y minus 7. State the coordinates of the vertices of the new triangle A prime, B prime, C prime. All right, so let's first talk about, because there's a lot of stuff that's new in this little problem, and I don't want to gloss any of it over. First, let's talk about the transformation rule. This is a nice algebraic rule that basically just says, hey, no matter what your xy coordinate point is, I want you to transform it by taking its x coordinate and adding 5, and taking its y coordinate and subtracting 7. Now what that means is that a given point, like point A, right, which had coordinates at 2, 9, will get mapped. That's what that arrow means. Point A is going to move to point A prime, and specifically it's going to move to a point where it's 2 plus 5, right, that's the x coordinate, is 2 plus 5, and then 9 minus 7, right? So A prime is going to be at the point 7, 2. Very often, when we map a pre-image to an image, if the original sort of point is A, then we have A with a little mark. It looks like a little apostrophe mark. We call it a prime, all right? And if there's 2 of them, we call it double prime. And 3 of them, we call it triple prime. Anyway, don't worry about that for right now, but A at 2, 9 went to 2 plus 5, because that's the rule, and 9 minus 7, because that's the rule. What I'd like you to do now is use the rule to figure out where B goes, where C goes, plot them, right, in the plane, right? Well, actually, that's part C. So just figure out where B and C go, right? And then in letter C, we'll actually plot them and draw the new triangle. Go ahead and spend a few moments doing that. All right, let's go through them. Well, first, let me kind of go back up to here. Point B was at 4, 13, right? So that pre-image point gets mapped to B prime. All right, 4 plus 5 is going to be 9, and 13 minus 7 is going to be 6, so B prime is going to be at 9, 6. And then let's take a look. C is at 8, 8. So let's do C, which is at 8, 8, will get mapped to C prime. The first 8 we're going to add 5 to, and that's going to be 13. The second 8 we're going to subtract 7 from, and we're going to get 1. All right. So we've got the vertices of our new triangle at 7, 2, 9, 6, and 13, 1. So we're ready for letter C, where it says, draw a triangle A prime, B prime, C prime in the coordinate plane. This is known as the image of the transformation. All right, well, this is as simple as it's going to be. I'd like you to plot A prime, B prime, C prime. Make sure to label them with a A and a little mark, a B, a little mark, C, a little mark. Then take your straight edge, connect the 3 points, and that will be our image triangle. Why don't you pause the video now and go ahead and do that. All right, well, let me go through it. I'm just going to scroll up just a bit so we can see it. Let's see, we have A prime at 7, 2, so that's going to be right here, right? We've got B prime at 9, 6. So that's going to be right here. And we have C prime at 13, 1. Right, then we're going to take out our straight edge. Again, a faster process for you than likely for me. But I feel like I really have to have these things straight. Let me go up here real quick. And finally, it almost worked. There. All right. And that's my image triangle. This just drives me nuts. I can never leave my ruler kind of slanted like that. I don't know why. Okay, final question, letter D. Are the 2 triangles congruent? Use tracing paper to decide. All right, so the question was, really, after I did this transformation, a triangle got mapped to a triangle. That's awesome. The question is, are they congruent? Are they identical triangles? So what I'd like you to do is I'd like you to actually trace this one out like I've done in red, and then see if it lies directly on top of this one. Pause the video now and do that test. All right, well, hopefully you found the answer to be yes, because when I actually trace that triangle out and I put it down here, maybe it doesn't look the best, but it definitely lies on top of it. So the answer is most certainly yes. All right. And that's going to bring us to a very important topic on the next page. Okay. Transformations that result in images identical in shape and size to their pre-images are known as rigid motions. Think about what the word rigid means. Now, maybe you don't know, but maybe you got a teacher that's really rigid. Not your math teacher, somebody else, obviously. But rigid means unchanging, not willing to change, or kind of set in its ways, right? So a rigid motion is any kind of a transformation that doesn't change the size nor the shape of the object. In other words, it produces an image that is congruent to the pre-image. So, here we've got the Eiffel Tower, le Tour Eiffel, and, maybe I do something to it. Maybe I rotate it or something like that. this would be a rigid motion because ultimately speaking, this and this, even though they're in different orientations, they have the same size, they have the same shape. On the other hand, we can certainly have transformations of the Eiffel Tower that aren't rigid motions. So let's say I took this thing and I stretched it horizontally, right? But maybe I didn't mess with it at all vertically. All of a sudden we get an image of the Eiffel Tower that is not congruent to the original. It's not identical to it. This concept and this piece of terminology is exceptionally important. Rigid motions are transformations that do not change the size or the shape of the image, and therefore the image is congruent to the pre-image. Let's work with this a little bit more in the next exercise. All right, here we go. Back to the coordinate plane, exercise number 2. Square ABCD is shown below. A transformation is given by the rule x comma y gets mapped to 2x comma y plus 1. Letter A asks us to state the coordinates of the vertices of the pre-image. All right, so this is very similar to what we did before. What I'd like you to do is pause the video and write down the coordinates of points A, B, C, and D right up here. Be careful. All 4 points have very similar coordinates, but subtly different that will make a difference once we start applying that rule. Take a few minutes to write down the coordinates of A, B, C, and D. All right, here we go. Well, point A we get to by going left of the origin 3 and up from the origin 3. So point A has got coordinate -3, 3. Point B, on the other hand, we get to by going 3 units to the right of the origin and 3 units up from the origin. So point B has coordinates of 3, 3. Point C, right? We get there by going right 3 and down 3, so it's got coordinates of +3, -3, and D has coordinates of -3, -3. Again, it's very, very important. If you didn't get these completely right, I want you to go back and I want you to really think about them. You've got to be able to read off coordinate points from the coordinate grid. Now, predictably, let's take a look at letter B. Show where each of the vertices is mapped in the image, A', B', C', D', and then draw A', B', C', D'. All right, let's do this together for point A, and then we'll have you do points B, C, and D on your own. So here we go. A, which is at -3, 3, where does it go? Well, it goes to its image point A'. And what does the rule tell us? Let's really take a look at the rule. The rule says, here, take the x-coordinate and map it to 2 times the x-coordinate, right? That's what 2x means. So if we start at -3 and we do -3 times +2, we will get -6, right? That's just what I get when I multiply -3 by +2. On the other hand, the y-coordinate, I'm going to take the y-coordinate and just add 1 to it. Well, I'm starting at a y-coordinate of 3, and when I add 1 to it, I should be at a y-coordinate of 4. So there it is. There's the image of point A. A' is at -6, 4. Now be careful a little bit when you add 1 to the y-coordinate, especially when the y-coordinate is -3. Hint, -3 plus 1 is not -4. Anyway, why don't you pause the video now and work through where points B, C, and D all get mapped to. All right, let's do it. Here we go. So B, this is probably the easiest one, 3, 3, right? B', when I multiply the x by 2, I'm going to get 6, and when I add 1 to the y, I'm going to get 4. Pretty easy there. On the other hand, C, which is at 3, -3, this gets a little bit trickier because although multiplying 3 by 2 and getting 6 is simple, -3 plus +1 is actually just -2. Right, there's where we got to be careful and not say -4. On the other hand, D, which is at -3, -3, right, that will go to D', which will be -6, -2. We were also asked to draw A', B', C', D'. So let's go ahead and do that. A' is at -6, +4. So there's A'. Right? B' is at +6, +4. C prime is at positive 6, negative 2. And D prime is at negative 6, negative 2. Now I could take out a straight edge right now and kind of connect these, but I'm just going to freehand it to save ourselves a little bit of time. I really, again, should use a straight edge, but good enough there. All right, and there is our image. Letter C should be an easy question to answer now. Is this transformation given by that rule a rigid motion? Explain. All right, well, go for it. Pause the video now and just answer that simple question. Yes, no, is it a rigid motion? And then explain your choice. And the answer is most certainly no, right? Now, there is a lot of different ways that you can justify no. You know, one way you could justify no is you could say, well, I traced out A, B, C, D on a piece of tracing paper and it doesn't lie directly on top of the image. You could go with that rationale. You could also go with a rationale, and I like this a lot. A, B, C, D is a square, and yet A prime, B prime, C prime, D prime is clearly not a square, right? Right? These two shapes are simply not the same. They're both rectangles, but ABC is a square, whereas A prime, B prime, C prime, D prime is most certainly not a square. And I think that's where I'm going to go with. I'm going to say ABCD is a square, while A prime, B prime, C prime, D prime is not. By the way, please be careful. You know, it would be very easy to say something like A, B, C, D is a square while A prime, B prime, C prime, D prime is a rectangle. Now that would be true, but all squares are also rectangles. So saying A, B, C, D is a square and A prime, B prime, C prime, D prime is a rectangle, that doesn't explain them not being congruent, given that all squares are rectangles. But saying that A, B, C, D is a square while as its image A prime, B prime, C prime, D prime is not, that's perfectly good. All right, let's take a look at one last problem. Now, there are lots of transformations that we're going to expose you to in the next few lessons. One of them is going to be a reflection. So we just thought we'd throw in a reflection right at the end, given that we're going to be doing those in the next lesson, so that we could get a little work with tracing paper, which you're definitely going to need on this one. And we're also not in the coordinate plane here, right? Everything that we've been doing so far with those transformation rules have been in the coordinate plane. But all of these transformations actually can also occur in what's called the Euclidean plane, so no coordinates whatsoever. Let's take a look at exercise number 3. Right triangle DEF is shown below along with segment AB. Use tracing paper to help with this problem. Letter A, trace both triangle DEF and line segment AB onto the paper. All right, so I literally want you to take your tracing paper, hopefully it's not this big, that's how big I would need, and I want you to lay it down on top of this picture. I then want you to trace out DEF, and I would suggest labeling DEF on your tracing paper, and also trace out line segment AB and also label A and B, okay? Take a moment to do that. All right, now what we're going to do the reflection is really kind of cool. Take your tracing paper and literally flip it, right? Just flip it over. You know, and then if you flip it over, it's going to look something like that. And then what I want you to do is lie AB on top of itself. Again, probably easier for you to do than for me to do, right? Once you lie AB on top of itself, then letter C, draw a triangle D prime, E prime, F prime after a reflection across AB. Well, the whole point is, right, this now is where DEF is going to lie. So, you know, I could take my pencil out, trace this thing out, right? This would definitely be E prime. This would be D prime. This would be F prime. And in fact, one nice way to do this is because if you're using pencil, not pen, pencil works really well on this. If you just kind of trace over that image, then the carbon from the pencil will actually kind of make a light image of that on your paper. And then when you pull this away, you can always kind of draw it in a little bit darker. But there is that image. Not surprisingly, right, a reflection is a rigid motion. Right? It's a rigid motion. If we now took this thing, we would find that these two triangles are absolutely identical to each other in terms of their angle measures and their side length measures. We're going to do more work with reflections in the next lesson, but let's summarize this one. All right, so today we looked at transformations, and all transformations are rules that take a figure in the plane and they map it to another figure in the plane. The original figure is called the pre-image and the final figure is called the image. Oftentimes they have vertices that have the same letters, but whereas the first one might be A, B, C, the second one, the image, might be A prime, B prime, C prime, right? We saw that some transformations preserve both the size of the object and its shape. Those are called rigid body motions. And when you have a rigid motion, then the image and the pre-image are congruent to each other. We also saw a transformation that took a square and changed it into something that was no longer a square. So not every transformation is a rigid motion, but the most important ones typically are. And we're going to look at reflections, which are an example of a rigid motion, a lot more in the next exercise. Not in the next exercise, in the next lesson, because we're done with this one. No more exercises in this lesson today. I'd like to just thank you for joining me, though, for another NGen Math 8 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.